Welcome to you all. I am Luca Gemma, a PhD student for the Materials, Mechatronics and System Engineering at the University of Trento, and today, together with my advisor, Professor Davide Brunelli for the Industrial Engineering Department, and with my co-advisor, Dr. Martino Bernard, and together with Dr. Mher Ghulinyan, both for the Center for Materials and Microsystems at Bruno Kessler Foundations, namely FBK, we developed a work within the COSI-QP project entitled Analysis of Photodiode Sensing Devices in a Photonic Integrated Chip Solutions for Quantum Computing. But let me just jump straight to our work. I'm happy to present you our work on analysis of photodiode sensing devices in a photonic integrated chip solution for quantum computing, submitted for the IEEE Sensors 2020 conference. So quantum computing can really be a meaningful revolutionary technology in different and several fields. For example, in big data or artificial intelligence, as the presence of a superposition state in a quantum bit called qubit allows for jumping from exponential computational time of nowadays standard AI architectures to linear time. So a huge leap in the computational speed and thus in the computational time. And another one surely will be the encryption strategy and techniques, because nowadays they revolve mainly on factorizing larger numbers. For example, the RSA, one of the most broadly diffused algorithms, will be broken with no effort with a quantum computer. On the other hand, quantum computing could also ensure safe encryption with the quantum key distribution by exploring the fact that, according to quantum physics, the mere fact of observing quantum objects perturbs them in an irreparable way. Hello, Schrödinger's cat. So essentially, by observing the integrity of our data, you will be able to see and detect a theft in your data. Long story short, there are different ways to build a quantum computer, and many big companies are now pushing in this horse race, and they're exploiting different technologies to try to achieve quantum supremacy. For example, Rigetti and IBM are pushing with the superconducting circuits. There are topological systems exploited by Microsoft or photonic systems exploited by PsiQuantum, trapped ions used by IonQ, or finally the quantum annealing by D-Wave. So as you see, there are different ways, different routes to build a quantum computer and to achieve quantum supremacy. In our study, we're going to show you our chosen solution, so a photonic system, and especially a PIC. So a photonic integrated chip solution, namely a PIC, exploits quantum optics to apply quantum mechanics to photons, addressing the light properties of photons and demonstrating some kind of counterintuitive characteristics of quantum mechanics, such as entanglement and teleportation. So the information can be encoded into photons' degrees of freedom, and generally speaking, PICs exploit quantum optics to apply quantum mechanics to photons. Photonic integrated circuits were proved as a concrete possibility for building quantum computers in several papers, such as the one listed here, coming from Annoni et al. And Zhu et al. And further works were done by Qiang et al. And Harris et al. But still, such systems rely mostly on off-chip resources and detectors. And there is where we come. So we wanted to contribute by providing a characterization on silicon photodiodes as output detectors devices embedded in the very chip, so not relying on off-chip devices and solutions as we have seen before. This study comes after our previous study on a characterization on titanium nitride thermistors. Generally speaking, in quantum photonics, one of the main building blocks, if not the most important building block, is the beam splitter. as it represents the interaction between two channels. In such component, you can achieve different split ratios for the wave traveling through the waveguide. So you can get, as you see in the image on the left, a 50-50 split ratio, full transfer or no transfer. But we decided instead to use a more complex block called Mach-Zehnder Interferometer, namely MZI. This block was essentially obtained through a cascade of two beam splitters. And in fact, getting ideal split ratios with imperfect components is not a trivial task. And thus, at the cost of a more complex structure, we got more robust beam splitters and also the ability to fully control 2 degrees of freedom, the amplitude and the phase. So in our previous chip, we've chosen this approach, so adopting these MZIs to full control, as I said, the amplitude and the phase. And in this study, we aimed at fully characterizing silicon photodiodes to use as detectors embedded in such architecture. So for the architecture, we get non-stoichiometric silicon nitride for the photonic material. Then we have a silicon oxide layer above and below the photonic layer, a silicon wafer for detectors with epitaxial layer. And finally, the peak is realized in LPCVD and PECVD silicon nitride and oxynitride, respectively. So here we can appreciate our results. First of all, let me show you the IV curve near the breakdown voltage. So we inspected the dark condition IV curve to estimate the breakdown voltage. 6 silicon photodiodes were tested, and we evaluated the breakdown voltage closely to -29 volt. Then we tested also the dark condition IV curve to estimate the forward current, again with 6 silicon photodiodes, and all photodiodes were capable of bearing a current intensity of milliamperes without damage. Then here we tested also for the bright condition IV curve, so again 6 silicon photodiodes with normal incidence illuminations, but we tested with different illumination conditions achieved by changing the illuminator current and the optical zoom of the microscope through which the light beam passed. And as you may notice, the flux is roughly proportional to the illuminator intensity times the zoom factor squared. Then here we have the current intensity for null voltage bias, so the photovoltaic current against illuminator intensity. Again, we tested with the 6 silicon photodiodes and against the illuminator intensity, as I said. And as you may notice, again, here it is roughly linearly related to optical intensity. Finally, we also inspected the spectral responsivity in the visible and near infrared region. We tested this time with the 3 silicon photodiodes. We first measured the optical power flux on detectors, and then the measured photocurrent was also normalized on the power. And even if detectors had different, indeed, active areas, the normalized responsivity is the same. So, to conclude, we were able to produce successfully and characterize successfully silicon photodiodes, which will be used as detectors in our future photonic integrated circuits. And future work will involve the design and test of an electronic control system with feedback solutions to control the peak, looking at both linear optic and quantum regimes. And well, future challenges will be the design and synchronization of the multi-channels acquisition and reaching low latency in the response of the entire system. So, thank you for your attention. Have a nice day.